I got cut off at my cool AC/DC joke. So sad. All right, AC/DC. Anyways, stands for direct current and alternating current, okay? Electron flow happens because of the attraction or repulsion between the charges. So you remember when I used the balloon and I got the static in my hair and then I moved the Coke can along my desk, right? That is the attraction or repulsion of those charges. It allows it to move, okay? So there's a couple things when we get to electricity you need to understand. Some terminology, some SI units, okay? Volts, current, and power. All right, let's start with voltage. Voltage is determined by how great the electrical charge is between two objects. The more negative or positive that they are, the stronger your attraction will be, okay? So think for a second of a hose, right? If you've got a hose and you're spraying water out of it, it can either trickle out if you don't have it turned on very fast, right? And if it's not coming out very fast, there's a way to increase the flow, and that's by putting your thumb over it, right? And that will cause it to spurt out a lot faster. That's a good example of voltage. It's that flow, how fast things are flowing out of, the pressure, excuse me. It's the pressure of how things are coming out of that garden hose. So the SI unit of voltage is the volt. It's named after Alessandro Volta, who invented the battery. We've learned about him already, so we're not going in detail there. Current, on the other hand, think of current as the flow, okay? How fast it's flowing. Now, current is the number of coulombs of electric charge that pass a given point. So imagine my finger is the point, right? As the current goes past, how many electrons are going by this point in 1 second? That is your current, okay? The SI unit of current is the ampere, which is the amp, okay? Named after Andre Ampere, who pioneered the study of electromagnetism. So think of current more as the rate of charge, in other words, how fast it's moving, not the actual total amount of it, okay? So imagine you have like 10 gallons of water you're passing by this in that hose past my finger, right? Current is not the 10 gallons. Current is how much of that 10 gallons is passing my finger in 1 second, okay? Now, power is simply voltage times current. And you can use that little triangle thing there. We've done this in class before, where if I want to figure out what, current is, then I cover up the I, and then I do power divided by voltage. If I want to figure out what voltage is, then I cover up the V and I do power divided by current. And if I want it the other way, if I want to know what power is, it's voltage times current. Okay, so don't forget about that triangle. There are some application questions that talks a little bit about kilowatts per hour. You can read in that in your text. But there are some applications on 349 asking you to apply this, okay? So I want you to do those and submit them in with your homework at the end of this lesson, okay? Now, in order to understand resistance, you have to understand what a conductor and an insulator is, okay? And I'm not sure actually if you guys learned about this in 6th grade. I know the current 6th graders learned it, but maybe not you guys, okay? Conductors are material in which electrons, when the current flows easily, So conductors, they like the electrons moving. They have no problem with it. The electrons just go, okay? Atoms have a weak hold on their outermost electrons. Now, if you remember what substances have delocalized electrons, where they're not really holding on to their electrons, they don't care if they go from one atom to the next, you would remember that is metals, okay? So examples of this would be silver, gold, copper, aluminum. Those all allow the electrons to flow freely. So if you want electricity to flow, you're going to want to use a copper wire or an aluminum wire, depending on what you're doing, okay? Insulators are materials in which the current does not easily flow through. The electrons are locked into place, so they can't travel from one atom to the next. Therefore, they can insulate things from electricity. Things like rubber, glass, wood, porcelain, plastic, all those things are good insulators. So a lot of the times you'll see like a cable, like look, my computer cable here, right? Inside of this are a bunch of copper wires to allow the electricity to get to my computer. But around it is this plastic that keeps me from not getting zapped, right? Which is why it's not good to keep cords on, like to walk over cords a lot, because they'll start to fray, the plastic will fray, and then the cords will get exposed, and then all of a sudden you can have electrical discharge that happens and you can start fires. Our computer cart actually at school has been taped a couple of times because the wheels keep rolling over those wires, the plastic, and the plastic is actually broken in a couple of spots. So next time you're at school, you can check that out. I know you totally will. All right, semiconductors, okay, they're not actually good insulators or good conductors. They allow the current to only go in one direction, but not the opposite direction. So this is really good for electronics, where we just want it to go in one direction. Silicon and germanium are both good examples of metals, or semi-metals, I should say, that are semiconductors, okay? So we learn all that to understand what resistance is. Resistance is the amount that the electron flow is hindered. Because we live in a fallen world, we have things that it doesn't work perfectly, right? If you feel my computer right now, there is some heat coming off of my computer. That's that joule heat that builds up because it's not flowing easily. Some of the electrons are being hindered. Now the SI unit for resistance is an ohm, okay? A wire with a resistance of 1 ohm requires 1 volt of pressure to force 1 amp through it. Okay, that's just the mathematical formula there. We're going to talk about that again when we get to Ohm's law in just a minute. There are 4 things that can affect resistance, okay, the type of material you use. It talks about it in the textbook in a little bit more detail, but certain materials conduct electricity better than others. Like we talked about, copper and aluminum, they allow electrons to flow a little bit more easily than the gold and silver do, okay? Plus they're also not as expensive. The diameter of the conductor, how thick is it? Is it a thick diameter or even thinner diameter, right? How long is your conductor? Is it long? Is it short? That's going to affect the resistance. And then finally, the temperature, okay? Now, because of resistance, we get this joule heat, which it talked about in the textbook, okay? Some devices, we really like joule heat, right? Like my hair dryer, I want it to give me joule heat because it heats up my hair and dries it quicker. Some things, like another one would be the toaster, right? We talked about back in chapter 5 how the toaster lights up and gets red and those wires heat up. That's that joule heat and we like it, okay? Some things we don't want them to have that joule heat. And so, for instance, computers are one where we don't want a big buildup of joule heat. It's not great for the computer. So there are what we call superconductors, okay? Superconductors is a material that allows current to flow through with no resistance at all. So it's extremely useful because the amount of energy you're putting into something is the amount of energy you're getting out, okay? It has no joule heat, therefore, and it can store large amounts of energy efficiently. So that's great. Why don't we use superconductors more often? Well, in order for superconductors to work well, they need to be lowered to a really low temperature. And so that really cold temperature makes it pretty much impractical to use, okay? So that's another way that we can improve science in the future, is figuring out how maybe other things that are superconductors that don't require being cooled to a super low temperature, or figuring out a way to still use them or create that super cool temperature without it being super impractical, okay? All right, the final thing is Ohm's law, which is, again, talking about this resistance. We have another one of these little triangles here, okay? So the V at top is the voltage, I is the current, R is the resistance. So it's similar to the one up top. But current flowing through a conductor is going to be directly proportional to your voltage and inversely proportional to your resistance. In other words, as your current goes up, what's going to happen to your voltage? It's also going to go up because they're directly proportional. They're going to go up same amount, okay? If your current goes up, what's going to happen to your resistance? It's going to go down by the exact same amount, okay? So current and voltage are directly proportional. Current and resistance are inversely proportional, okay? And that's essentially what Ohm's law is and says. And there's a chart there on 352 to help you understand that a little bit more if my little fingers wasn't enough, okay? So resistance is any electrical device designed to add that can't be right, that makes no sense. Hold on. That last blank. Oh, a resistor. I wrote it down wrong. A resistor is an electronic device designed to add resistance to a circuit, okay? This prevents large amounts of current passing through. Your textbook shows you probably, if you've ever taken apart an electrical device, you've seen one of those little guys, okay? That is to prevent too much current coming through, because if too much current gets through, it blows up. All right, which we don't want. All right, so we are going to talk tomorrow or in the next lesson about circuits, and then I've got some fun activity you can do with that. So something to look forward to. But if you guys have any questions, I do want you to do 1 through 3 on the application, 249. And then I want you to do all of the section review questions, 1 through 10, and the think, but you can just write short answer. You don't have to write everything out, okay? So yeah, I miss you guys. I love you, and I hope you're well, and mwah, bye-bye.